In this follow-up example, we're going to see how our contingency table, our frequency table with probabilities and empirical probabilities, corresponds to a chi-squared test. A chi-squared test is often used to evaluate whether or not two or more variables, so in this case we have our starch variable and our side dish variable, it asks whether or not they operate independently. That is, does the probability of getting a particular starch depend on the probability of having a particular side dish? And conversely, does the probability of getting a side dish depend on the probability of having a starch? Or can we just kind of randomly choose any one of these and one of these and it works out? More formally, it is testing the AND rule, or the multiplication rule of probability. So before going too far, it's probably worthwhile reviewing the AND rule, the multiplication rule of probability. We'll use the bread and soup example I have here. I think the first thing we're going to do is actually change this top one around. Let's just go rewrite it. So the probability of, if I can spell this correctly, the probability of bread and soup. Now notice the probability of soup and bread put us in this cell here. So it's the intersection of the bread and soup. So 9 divided by the 60 days we could have had that. That's where we got that 0.15. So here we have listed soup and bread. I'm changing that around just for teaching purposes, for the probability of bread and soup. Notice it's still 0.15 because we're still talking about this cell, the soup and bread intersection. So it doesn't matter which order we put it in at this point. So our probability of having bread and soup, according to the AND rule, or the multiplication rule of probability, is equal to the probability of bread, and we multiply that times the probability of having soup, given that we are having bread. So that is the formal AND rule of probability. And there are some things to point out. So probability of bread and soup, we've already said that the bread and soup means the same thing as soup and bread. It doesn't matter what order that goes in. Probability of bread, well, we've kind of learned how to calculate that. We're just going to take the number of bread days and divide by the total number of days that we could have bread. That's pretty straightforward. It's the same as probability of noodles or probability of soup. Then we see this kind of weird one that has the, I think that's called a pipe in it. The probability of soup given that we've had bread. Well, the whole reason for changing this around is because we've already seen soup given bread. We calculated it down here. And if you remember from the previous video, this was a bit different. We still take the soup and bread intersection. That is still what we care about. But instead of dividing by the 60 days we could have had it, the information that we have to have bread means we take the 9 days of soup and bread and we divide by the 14 days in which we actually had bread. And that increased our probability. So that caveat, that condition of having to have bread drastically changed the probability from when we don't have that condition. So similarly, when we use or invoke the AND rule of probability, when it comes time to calculate bread and soup, we need to account for that condition. So if we're having bread, when it comes time to deal with the soup probability, we have to take into account the fact that we have already had the bread. In this case, we have those numbers, so we can just calculate that directly. We'll do it here. The probability of bread, this we don't have, so we'll calculate it right now. Probability of bread is the 14 days, 14 bread days, divided by the 60 days we could have had bread, no restrictions. And we multiply that times the probability of soup given bread. Well, soup given bread we've already calculated, but let's just do it longhand so it's familiar. So there's our soup and bread. There's soup and bread, the two things we care about. But instead of dividing by 60, we have to calculate by the bread days, because that is our condition, that is our limitation. So it shouldn't matter according to the order of operations, but just so it's clear, there's our first probability, probability of bread, and we'll multiply that times our second probability, soup given bread. And so we see the probability of bread and soup given bread is 0.15, which is the same as we calculated here, the probability of soup and bread, 9, divided by total number of days, 60 days. So that has to happen. So we used the rules of probability, which kind of separated them out, and we applied it, including the conditional statement here. And that has to give us the same thing that the actual raw data gives us. Now, we can ask the question, and this is really what the chi-squared test does, of, well, what happens if we didn't account for the soup given bread? What if we assumed that bread operated independently from soup? So this given bread didn't matter. So the probability, I guess the other way of saying that, if we write this out, the probability of soup given bread, that would be the same thing as the probability of soup. That is the condition of independence. So if the bread doesn't have an effect on soup, then the probability of soup given bread is just the probability of soup. So we can calculate this also. It's kind of doing what we did here with the noodles and soup, but we're just changing this last one a little bit. So let's go recalculate this. So the probability of bread and soup, this is still what we want to know, is equal to the probability of bread. And assuming independence this time, it is times the probability of soup. So we're kind of invoking this, that soup given bread is the same thing as just the soup. There's no interaction between the two. And so now we can fill these numbers in and see what value we get. The probability of bread is the number of bread days divided by the total number of total number of days we could have had bread, no restrictions, and then we multiply that times the probability of soup. Let's go put these in parentheses also, just to be good about it. And multiply this times the probability of soup. So here's our soup days. We had 29 of those, divided by the total number of days we could have had soup, no restrictions. So if we do that, we see, assuming independence, the probability is 11%. Well, that 11% is not the same thing as the 15% that we got when we specifically accounted for an interaction. If there was no interaction, so if this was a safe assumption to make, and remember this assumption is the variables behave independently, there's no interaction between the two. If this assumption was correct, then these two values should be the same. They are not the same, which on some level indicates, well, that assumption of independence is incorrect. There is a dependency, there is a relationship, there is an interaction between the two variables. So what our bread probability was did have an effect on our soup probability. So we can see those numbers, but we can also see that, well, this is a sample, and if perhaps in 2 months, another 2 months went by and we had another table, we could do this again, and my probabilities would be different, and I would get different numbers. So that idea of, well, here's a probability, but based on a sample, what is the long-term result? What is the truth of this? That is what a chi-squared test gets for us. It does this comparison of here is the probability under the assumption that the variables are independent, there's no interaction. And here's what the data tells us. Is this close enough to say, yeah, in the long term, these would actually be the same? And it's just a random variability. It's had an artifact of it being a sample that these are different now. Or is there a small enough chance that this would happen randomly? And in fact, these probabilities would be inherently different in the long run, and our assumption of independence is violated. That is not a good assumption, and these numbers will never be the same, even if we took a lot of samples. That is the question that a chi-squared test answers in this particular case. So let's go through the chi-squared test. No, let's actually save that for the next video.